you for joining us today for this webinar. This is being recorded, so we wanted to let you know already so that you know that you can um, look at this video afterwards and reference it as you go through. And also the presentations are going to be shared with the audience. A few technicalities before we get started. We're on the GoToWebinar setting, so this is how the panel should look like. You have the option of muting and unmuting yourself. As attendee, the default setting is you're going to be muted, but if you want to raise your hand and maybe pose a question to the presenters as we go through, please feel free to do so. We will have some moments during the event where you will be able to pose this question. So in any moment, as we go through, you can always put your question in the question box, and we will make sure to note it and to share it with the speaker as soon as the presentations are done. We will have a short Q&A of around 3 to 5 minutes after each presentation. And why are we having this meeting? So what is the context of it? Well, this is as part of the Dynaxibility4CE project, which is an Interreg Central European funded project. Was just finalized last month, and we're sharing some of its main outputs today. And the goal of the Dynaxibility4CE project and its main objective was to learn and bring together results from a series of projects that have taken place or are taking place in the different European funding programs. As you can see here, we've worked with several projects in the different areas. And this is just a selection of those that we've cooperated with. And to take those lessons learned around how to plan for mobility innovation and help cities in implementing those tools and lessons learned towards the development of action plans and specific roadmaps on how to plan for particularly the topics of automation, mobility as a service, and urban vehicle accident regulations. The name behind it, so this term Dynaxibility or Dynaxty, it comes from this idea of being able to balance the dynamics of these fields, these innovative mobility planning fields, and its complexity to find a good area where you have enough flexibility to manage these uncertainties that come with this type of fields, and move organizations from a traditional setup to this level of Dynaxibility where they're able to plan for the topics that we're talking about today. So find that right balance between the long-term vision and adaptability. And as I was mentioning before, its objectives particularly have been to develop and further contextualize SUMP guidance in relation to these three topics that I've mentioned before, that is connected, cooperative and automated mobility or CCAM, urban vehicle access regulations or UVAR, and mobility as a service or MaaS. And to provide trainings and tools to partner cities and also cities around Europe and the world on how to increase their capacity to address these topics in mobility planning and develop action plans towards its implementation. For all of these outputs, please visit our website. You can find it in the comment section below. And as well our SUMP Competence Center, which we will be introducing as final in the final session, the closing session of today's webinar. Now, this webinar in particular means to share some of these results in relation to the testing of some of these innovative solutions through two main methods. So one of them, modeling, simulating specific services, and the other one, how to test things on site, these types of solutions, and to effectively engage with stakeholders and users on this type of pilot or living lab setting. And this is in relation to two of the main Dynaxibility outputs. These are the tools, one guideline on MaaS and CCAM ready transport model, and the other guideline on new stakeholder engagement formats in this type of experimental design and living labs. So we'll be looking at a few examples of how this can be implemented and letting you know where you can find the tools as soon as they're published. And of course, to engage with the participants and learn from their interests and needs of supporting these topics. So the agenda of today's webinar is that after this short introduction, I'm going to be providing, let's say, a context setting in the topic of transport modeling for mobility automation. And then we will hear from the specific case in the Stuttgart region study that was done on the integration of autonomous ride-sharing services with public transport by the University of Stuttgart. And it's going to be Emily Richter who's going to be telling us a bit more about this and how they did this study. We'll have a short Q&A and continue then with the topic of stakeholder engagement formats and how to run this type of experimental design settings with stakeholders and users. This by our colleague Gabriele Grea from Redmond, project partner of Dynaxibility4CE. And he will also be presenting the specific case of living lab in the city of, well, I cannot pronounce this, Salagerceg, and how they advance the stakeholder engagement and co-design of a demand responsive transport pilot project. So these are our project partners, and without further ado, let's get started with our first presentation. Why are we talking about how to plan for automation, and what is the context of this effort in Dynaxibility and in the projects that we've been working with and following up? Well, we have one of our main goals basically has been to increase the capacity, the capability of authorities and stakeholders to make informed decisions about the topic of automation in mobility, about CCAM. And to do that, we first did a analysis of what the needs were, what were the main gaps in knowledge, and based on two main documents that we've been working on previously in the Coexist project, which I'm going to be talking about today as well. Those were the road vehicle automation in sustainable urban mobility planning practitioner briefing, and the automation ready framework, which presents a conceptual approach on how to address these efforts of planning for automation. Based on this, we performed this gap analysis and learned a bit of what were the main let's say areas of support where authorities needed to increase their skills and capacities to be able to address this topic of mobility automation. And one of the main ones and a recurrent discussion has been about how to implement scenarios and to assess service models. And that has a lot to do with some of the other key topics that have to do with a beneficial and sustainable future for CCAM in our cities, and is around how to make these solution designs user-centric, how to understand and effectively respond to those societal needs, how to manage a correct integration with public transport, and all of this required a robust impact assessment framework and methodology including different types of indicators, not only mobility-wise, but also socioeconomic, environmental, and so on. So with this in mind, the topic of modeling becomes very central, being able to test service models and specific solution scenarios in a topic as broad as or let's say as uncertain as mobility automation, where very few um, um, actual services can be tested, and where how this is going to be looking in the future is rather uncertain. So some of the main challenges and support needs around how to perform this modeling of automated mobility was understanding what the technical implications of each of the different functionalities of automated vehicles are, and how they can affect vehicle behavior, and how their interaction can also affect traffic flow or the demand performance, for instance, how travel performance, safety, space efficiency would be changed by this. Also, how to adequately define the modeling parameters, and also what assumptions need to be made in defining the scenarios to be tested, and evaluating the user preferences and expected travel behaviors as well. And looking into what we've worked before in the Coexist project, this provides a good introduction on the modeling approaches that we have analyzed and we're working with now in Dynaxibility. And we're going to go through a bit of these results from Coexist now as introduction to our modeling guide in Dynaxibility, and what will be presented next by our colleague Emily Richter from the University of Stuttgart on a particular use case in the Stuttgart region. So going back to this modeling approach in Coexist, which is building up into this scenario analysis. Our first questions back then in the Coexist project a few years ago were around how to analyze and how to model specific behaviors of automated mobility. And there you can think about the SAE levels as an initial description of the type of automation that we might look at. But this is very much focusing on to what extent the vehicle can drive itself, where it can be driven in automated functions, and what are the responsibilities of the different let's say players in the moment, the driver, the vehicle itself, the manufacturer, and so on. But it doesn't really go on the specifics on how the vehicle is behaving and what that can mean in terms of traffic flow and so on. That's why in the Coexist project, the focus was on how the vehicle can be functionally described in terms of its operation, its behavior, without thinking of the technologies that would allow for this to happen. To do so, a few driving logics were defined. And politically described here, we have the rail safe one, the cautious one, the noble, and the all-knowing driving logics. You can see there the descriptions, but without going much in detail, they would basically characterize a few options of how the vehicle can behave in relation to its level of automation, and in relation to how well it's connected with the infrastructure, and what knowledge it would have, how safe it would be, and what restrictions it would have. A few of the other, let's say, variables to consider were the market share of automated vehicles at the moment where the scenario is being tested, its capabilities, and the driving behavior, of course. So in Coexist, this was, let's say, managed by creating a framework where these variables were varied in different scenarios, and so that we can evaluate what their effects on the traffic were. So, for instance, in relation with the AV class and driving logics, you can see here how the different scenarios were built, and for each of these different road types, what type of um, AV class and what type of driving logic would be allowed to take place, where this could actually be tested. And the same with the penetration rate of automated vehicles, so how many vehicles are actually in the market at that moment. The AV share that was considered had to do with also the stage of introduction in a future scenario. And this would also be a good introduction to how these different driving logics were then modeled in Coexist. Basically, after running tests on an test site in one of our partner cities, city of Helmond in Netherlands, the Coexist project was able to develop a few default parameters for AV behavior in different settings, and then also relate that to the capacity and volume delay functions for the microscopic modeling. A few of these default driver logics can be seen in the slide, but the important topic behind it and what we're addressing in the modeling guide is what this means and how they can be still analyzed by someone who's doing this work of modeling an automated vehicle, and how to shift in depending of the situations that are being tested. And type of logics, you can see there the throughput for the options that are and in terms of course then the travel demand modeling. This also is something that was tested in the Code 6 project, developing functionalities to model such travel demand changes, and we'll see how this is implemented in a specific use case in our next presentation. But it's interesting, of course, to note here how such things, what are the parameters that needed to be considered, and this is addressed as well in our modeling guide, of course, how you need to think about the perception of time by the driver, how much more willing to drive longer distances could passengers be, and also whether the capacity of certain roads would increase or decrease depending on the type of vehicles that are in that moment on the and a good framework to understand these connections between specific traffic flow, then its effects on demand, and the type of services that we've studied had to do with an exercise that we did back in the Coexist project as well, where some of our twinning projects in the US had developed a framework to analyze, model, and simulate automated vehicles, and we did an exercise to apply this framework, which relates these different topics that I've been talking about, and study, okay, what is it that we're talking about and how they relate to each other. So this is, I think, a good way of understanding the different relationships there. On the bottom, you can see the operational performance level, and this is what we're talking about in relation to specific driving logics and how they interact in these heterogeneous traffic conditions, the different AV penetration rates, driving logic mixes, whether you're including platooning or not, and so on. And in the Coexist project, taking on this information and taking on the already developed functionalities in the Coexist project, we've been interested in learning from specific supply options. So moving into the green area, what are those new types of services? For example, on-demand services, road sharing, ride sharing, sorry, and how would this affect travel demand, travel choices, and scheduling? So this has been a few of the cases that have been tested in Dynaxibility. We have, for example, our colleagues in Leipzig who are running DRT pilot, an on-demand pilot. This is not yet automated, but is testing a new service, which the idea is to integrate it with automated shuttle project that they're working on now called the Absolute project, and to test in the future how this type of on-demand services can be also automated and what its impacts could be on mobility. And of course, the case of Stuttgart, which we will learn from in the next presentation, is also about seeing how these new types of services, on-demand ride-sharing of vehicles, can have an effect on travel demand in an area of the city. And finally, we have this network integration, so how the different multi-actor, multi-stakeholder ecosystem comes to play in terms of the operation, the planning of such systems, its interaction, its equilibration. And for that, we go back to the SUMP concept, and in the guide, we work with some of the results from partner projects like Momentum project and Horizon 2020 project, which also just ended. And they looked into what are those steps in the SUMP planning where this type of modeling needs to be taken into consideration, what are the steps that need to be made, and how to engage with the stakeholders involved there. So this is all what we wanted to present, that it's in this guide for CCAM and MaaS-ready transport model that Dynaxibility has produced. So you can find it soon in our website. The content of it, to give you a teaser, is presented in this slide. It talks about the different challenges and uncertainties of CCAM and MaaS modeling, this framework of analysis that we've been discussing, the different operational conditions and behavioral changes, and how we can think about these types of solutions for modeling. And then also provides an overview of existing tools and methodologies from the various projects that we've cooperated with, and that can serve for our audience to implement such efforts on the local level, with guiding materials, recommendations, as well as good practice examples and references. So with this, I would like to give the floor to Emily from the University of Stuttgart. Emily, thank you for joining us. I'll give you the option of sharing your screen. Okay.
Okay, you see it now? Or?
I can see it. No? Yeah.
Yeah. Okay. Very good. Okay. Yeah. Then welcome again from my side to my presentation on our study, which we did as part of the Dynaxibility program. Sorry. Yeah, so we wanted to integrate autonomous ride-sharing, or we did integrate autonomous ride-sharing services into public transport in a peri-urban area in the Stuttgart region. And yeah, I want to present to you now some of our modeling approach and some results we got. Yeah, so first the definition of terms, because those are not always the same. So if I say autonomous, I mean like fully automated and self-driving vehicles. And with ride sharing, I mean that independent travelers share a vehicle trip. And our ride sharing service is a part of public transport and does not compete with public transport. And it consists of two forms of ride sharing. Firstly, there is direct ride sharing, where ride sharing is the only means of transport from origin to destination. for a traveler. And then secondly, there is ride sharing as a feeder, where it is a feeder to buses or trains. So this is my agenda for the next few minutes, and I want to start with presenting to you our case study. So this here is our study area. It's called Schurwald, and it's east of the city of Stuttgart, within the Stuttgart region, and it has about 50,000 inhabitants. And in the north and in the south of the area are rails, and there are line routes of the regional train and the S-Bahn, for example. As modeling base line, we use the macroscopic travel demand model of the Stuttgart region, in which all the travel demand for the whole region is calculated. But our ride-sharing offer is only offered in the study area that's shown here. So in this area, in the Schurwald, we have in the baseline scenario, so the status quo, we have a quite good timetable-based public transport offer. It's mostly offered by buses. And yeah, they even have headways up to 15 minutes. So it's quite a good public transport offer, I would say, for such a peri-urban area. And nevertheless, we want to see what we can do with that, and we want to replace those buses within the study area with ride-sharing services. And this brings us in the ride-sharing services to around 600 bus trips that are replaced by ride-sharing, and this approximately equals 8,500 bus kilometers that are to be replaced with ride-sharing services. So here is what we calculated in our scenarios. First, the baseline, I say, was the macroscopic travel demand model of the Stuttgart region for the year 2030, as I already told you. And on top of that, we created a new baseline scenario, which is the same, but has a more disaggregated demand structure in the study area. So this is because we wanted to be able to better model the pooling of the ride-sharing trips. And in contrast to this baseline scenario, we have our 3 ride-sharing scenarios. In the first 2 scenarios, we are offering a ride-sharing service that has a maximum waiting time of 15 minutes for the ride-sharing passengers. And in the first scenario, the pickup of the passengers is at stops, and at the second scenario, the pickup of the passengers is at their doorstep. In the third scenario, we combine again the traditional public transport of 3 additional bus lines we implement again with a headway of 15 minutes, and additionally there will be a ride-sharing service with a maximal waiting time of 13 minutes for the passengers. We also had to come up with some basic assumptions about ride-sharing, and the first one is that it will be offered at the same fare as the public transport. And for example, in our ride-sharing vehicles, we have a capacity of 6 passengers. And the ride-sharing vehicles are also assumed to be self-driving, which is here in brackets because it's not really important for our modeling here, but only for the cost calculation, energy consumption, and so on in the end. And last but not least, we have also ride-sharing as a feeder to public transport. So here we need to consider a walk time of 3 minutes for the transfer, and we also consider a wait and buffer time of 5 minutes, which is because we will have some fluctuations in travel time with the ride-sharing feeder vehicle. And yeah, because we cannot know in advance for sure how many people we will have to pick up additionally. So the travel time of the ride-sharing feeders is not really easy to forecast. So now getting to our modeling approach. As I told you, we have a standard macroscopic travel demand model, and it follows the 4-step algorithm. The typical 4 steps of the 4-step algorithm are the trip generation, the destination choice, the mode choice, and the route choice. And it is often extended for the departure time choice. All of these choices are choices of travelers, and they stand in dependence of the supply quality, for example, of travel times, which again are dependent on the volumes of the road network, for example. And this extended 4-step algorithm we need to extend again in order to depict the ride-sharing services. We need to extend it by the steps for pooling of trips for ride-sharing and the vehicle scheduling. And we need to extend the supply of public transport because we want to implement ride-sharing into public transport. So the difference of the pooling and the vehicle scheduling step to the other steps I just told you, or which are the part of the traditional 4-step algorithm, is that the pooling and the vehicle scheduling are the decisions of the operators and not of the travelers. In the pooling step, we will, or the operators will decide which vehicle, which passenger request will go into one service trip of a vehicle, and then in the vehicle scheduling step, they will combine the service trips of the vehicles with empty trips, and therefore then get vehicle scheduled. And with the vehicle schedules, we are able to know how many vehicles are needed. But at first, I promised you that we disaggregated our demand structure in the study area to be able to model ride-sharing detours in more detail, and that we did spatially and temporally. Temporally, we changed the differentiation of the day from 3 time intervals for the public transport assignments, which were the morning and evening rush hours and the off-peak times, into 96 time intervals of 15 minutes each throughout the whole day. And spatially, we disaggregated the 18 existing traffic zones into 301 traffic zones, which then had a maximal size of 300 meters times 300 meters. After that, we needed to consider under which conditions ride-sharing services are offered in the public transport offer. And this we did for origin-destination relations, so for which trips are ride-sharing services offered and for which trips are conventional buses or train services offered. We differentiated this in 3 cases. The first case is for trips that are starting and ending in places that have a bus stop, and here the traditional timetable-based bus will be offered as public transport. Then we have case 2, which is for trips that are starting and ending within the study area and where at least one place has no bus stop. Here we will offer direct ride sharing for public transport passengers. And this is also the case if we are within our study area and a transfer would be required. Otherwise, then also direct ride sharing is offered. In case 3, we are looking at trips that are starting or terminating in the study area, and the place in the study area has no bus stop. In this case, we have ride sharing as a feeder to the train stations in the north or the south of the study area. And with all these, we are now able to calculate the travel demand for ride sharing services. The demand for direct ride sharing is relatively easy to calculate because it comes directly from the mode choice step, and it equals the demand for the public transport on those case 2 relations we just had a look at. Mode choice always needs input values, for example, trip durations, and these trip durations for direct ride sharing we get from a private transport assignment, where we assign the ride sharing vehicles to the road network. They are driving from ride sharing stop to ride sharing stop. Ride sharing as a feeder is a little more complicated to achieve, or the demand is a little more complicated to get because we will only get it from the timetable-based public transport assignment. And in this, the ride sharing feeder links are modeled as direct links from zones to public transport stops where the transfer from ride sharing to trains is happening. And as you can see here, we decided for each traffic zone within the study area to which stop in the north and the south of the area the ride sharing feeder will go. Through this, we can achieve a high pooling rate, for example, and we can decide on which train stops we might provide enough parking spaces, for example, for the ride-sharing feeder vehicles. So after that, we get our demand from our trip generation, destination choice, mode choice, departure time choice, and a little bit out of our public transport assignment. And this is followed by pooling of the vehicle trips, or pooling of the passenger trips into vehicle trips, and then the vehicle scheduling. And after the vehicle scheduling, we now know all the vehicle trips, and that we will be able to assign to the road network now in the route choice. And after that is done, and after our iteration process is also satisfied because there are no changes in travel times anymore, we are getting our results. And those results are, for example, the private transport assignment of the ride-sharing vehicles, which you can see here, differentiated in service trips, containing also the detours that are needed to pick up fellow passengers, and the empty trips of the vehicles. Also, we get some indicator values such as occupancy rates and detour factors. And I want to show you some more results. For example, the impact on travel demand, which can be seen here in the mode choice in person kilometers traveled. On the left side, we have the trips with origin and or destination in the study area, and on the right side, only the trips within the study area. I mainly want to show you here that the public transport share increases in our ride-sharing scenarios. The public transport shares always the dark brown colored areas. What we can also see, which is important to acknowledge, that when we are looking at the trips within the study area, we can see that ride sharing also influences the destination choice. So people are traveling longer distances because ride sharing makes that much more attractive. And yeah, then shortly the impacts on the transport supply for the operators. Here we see how many vehicle kilometers per day are traveled and how the required fleet sizes are. In solid color are the ride-sharing values, and in patterned the bus values. And we can see a similar tendency to the person kilometers, but as is expected, the bus is more efficient in pooling people than ride sharing is. But again, we need to consider that we have got a much more attractive public transport service by ride sharing than by bus services. And only because of that, we get such a high demand, and only because of that, we also need such many vehicle kilometers and such a high required fleet size. So it really is a trade-off here. And that gets me to the main findings of our study. So especially direct ride sharing is very attractive and leads to modal shifts. Also, the often hoped for modal shift from private car to direct ride sharing. But the attractiveness of ride sharing as a feeder, on the other hand, is limited because we always have this transfer and we need the buffer time. And in our scenarios, the pooling rate was always quite low at only about 2 person kilometers per vehicle kilometer. Therefore, we also had a quite high operational effort. And this is also then leads to higher costs, high energy consumption, high CO2 emissions. And those were always a little bit higher than in the baseline scenario without ride sharing. And this was also true for the scenarios where we assumed that autonomous and electric vehicles are serving our ride sharing services. So we really did a lot to make the public transport in the Schulwald really attractive, I would say, but the modal share of public transport is limited nonetheless. So even with a very good public transport service quality, we do not reach the public transport share of cities. And that is mainly because the car use in those peri-urban areas is associated with hardly any lost times because we do not have any congestion there. So to sum up, with ride sharing, we get kind of an individualization of public transport here because people do not need to wait as long. People do not need to walk as far as they would have with bus services, for example, and they do not need to share their ride with as many people. But the service comes to the cost of higher operational costs. So in the end, we need some compromise solutions, which need to limitize or this individualization. For example, people need to wait longer again, or ride sharing is combined with the classic timetable-based offers. And if you're interested more in detail about our results, you can find it here under this address. Unfortunately, it's in German, but I hope it would help you anyway. So thank you for your interest, and I think that was it from my side.
Thank you, Emily. It's a great presentation and a great study. We've definitely learned a lot from it. So thank you for your presentation. Maybe just one question from my side. As having done this work, what would you think would be a key recommendation of something to take into account when someone is starting to consider, okay, I want to test model such a scenario in my city, and I'm going to be using this modeling functionalities that have been developed, but maybe what they need to know from the particular local conditions, like how can the parameters be evaluated and shifted in terms of the willingness of users to take one or the other mode? Would this be something that would definitely require some sort of previous knowledge of their preferences, right? Or what would you recommend in terms of like preparatory steps before just thinking that they can just set up a scenario transport model and run it and find some good guidance from it?
Yeah, of course, that's one of the main problems with this kind of modeling, because we don't really know what will happen and we can't really calibrate our models. But yeah, if you're looking for the willingness to share, I think the way to model it really good and in the right way would be to have a previous survey and to get the parameters there, but it's really yeah, it's a lot of work. What we did there was we assumed that by being part of public transport, that the parameters don't change, and we didn't change the mode choice. I think a lot of problems occur when you're changing the mode choice step. But yeah, of course it was an assumption, and yeah, it's not a good one, or it is assumption. So, but it would be better to have conducted a really big survey. But
No,
yeah,
of course,
you need time and money and so on.
Of course, but in any case, I think that it's good to note how you can actually, make these type of assumptions, and that allows you to test different services under the same conditions. That does have very valuable conclusions that can be achieved even without having that very specific knowledge of how people will react to um, automated vehicles, which is usually one of the main things that I think authorities are doubting about. Like, okay, how can we even test anything if we don't know that? But I think it's good to show, like, okay, if you make some assumptions, you can actually see what the differences are between a series of scenarios, and that can guide you in your decision making already now.
Yeah, but I think it's kind of, yeah, it's difficult to say, okay, this will be the definite number of cars we will see on the road there, but it's already helps the modeling process. You have to think about so many details. You have to think about, oh, do I really want that all these vehicles go there? And then you see this train stop maybe isn't that well prepared to serve as many vehicles there. So I think it's already worth for thinking about all these yeah,
Absolutely. Definitely. So again, thank you so much for your presentation. I think we'll give now the floor to our colleague Gabriele Crea from Redmond, and we will continue with our next presentations.
Yeah.
Thank you, Emily, and Gabriele. Welcome. Thank you for joining us. So we going with the agenda, we will now hear from new stakeholder engagement formats for this type of experimental testing on site with pilot or living labs. And this has also been a focus of work in Dynaxibility. Making you a presenter now, Gabriele, you can share your slides. Thank you.
Yes, thank you very much, Daniel, for the organization. And so just a second, I already started my presentation. So as you said, we combined these two topics, and I'm going to talk about the guideline we have prepared for stakeholder engagement, which is focusing on the main topics, the core topics of our project. Therefore, includes all, let's say, the main relevant experiences and methods to be applied in order to successfully engage stakeholders and support participative processes in planning for CCAM, in planning for MaaS, in planning for UBA. Where did we start? When setting up the Dynaxibility project, which is a capitalization project, so builds on previous project outputs, for this specific element, we thought of moving from the experience of a previous project, which is called SharePlace, which was dealing with shared and digitalized mobility within the same framework of the Interreg Central Europe. These are the takeaways of the engagement process and of the engagement, local engagement guidelines, which SharePlace produced in 2019. And this is, let's say, our starting point, where you can already see elements connected to local engagement, to the analysis of needs and expectations, to the co-design process, to the definition of business models, and to the implementation of technologies, which represent basically the basis from which we start on our, let's say, development, focusing on our three topics, so entering into the specific of quite complex and quite forerunner experiments of engaging stakeholders in delivering mobility innovations, as it's in the spirit of the Dynaxibility4CE project. Therefore, why we developed these guidelines on top on the existing one, in order to focus on our three topics, as I said, so to accompany the collaborative process, which is at the basis of the planning, but also of the design and implementation of these mobility innovations. And how we do that? We do that working considering all the needs and expectations and the experiences which were ongoing during our project in our functional urban areas, which are engaged in the projects, and of course their stakeholders, with the objective also to support the process within the project, and of course to leave a trace beyond the scope and the time frame for future mobility innovators and mobility planners for innovative mobility. How are these guidelines composed? What are composed by? The central part, the core part, is a step-by-step guidance, which basically follows the SAM cycle and works around innovative methodologies, integrating them into the main prescriptions of the SAM cycle, with reference, of course, to CCAM, MaaS, and UVA. In order to elaborate this set of recommendations, we have analyzed and investigated in detail the experiences of our cities and functional urban areas, of course, but also a set of international good practices which are particularly innovative and are particularly fitting for our purpose. At the same time, we collected and analyzed, in order to provide a broader view, information and hints on national approaches on how to develop stakeholder engagement, specific methods and specific regulatory aspects or tools which have been implemented in some countries, especially in particular in the Central Europe area. So what are the findings, and how did we what did we decide to focus on? We decided to focus on three ranges of instruments or of experiences. The first one being the living labs and the co-design processes. The second one, the use and implementation, or the implementation and use of regulatory sandboxes, usually at a national level. And the third one is the citizen science approach, so the direct engagement of citizens in planning and developing solutions for mobility, starting from the analysis part, starting from the data collection and the processing of information. So engaging them as active part of the, let's say, scientific analysis at the basis of the delivery of mobility. So I would like to tell you a bit more about these three, let's say, core elements. So here are some definitions, but just to, let's say, define the perimeter of what we are talking about and what we are dealing with in our guidelines. So for living labs, we adopt a definition where living labs are ecosystems which are user-centered, which which deal with open approaches to innovations, and which make use of co-creation approaches in order to engage and extract value from the interactions with stakeholders. Living labs basically can be elements where the process of co-creation is facilitated and is fostered, and also in other cases environments, real-life environments where technologies can be developed, tested, become innovative services, and then scaled up, of course. What is co-design? Co-design is, of course, a collaborative process, creative process, which is, let's say, facilitated by experts, which engages a wide range of stakeholders in creation, in experimenting, in the learning process, and in the development of concepts, which then can be proved and tested within living labs. I make you a couple of examples, which you will find also in the guidelines as a useful reference, I would say, for, let's say, driving your local engagement process. So the first one is the example of the Helsinki Mobility Lab. It's a living lab established in the city of Helsinki, which basically provides three, let's say, kind of integrated approaches. The first one is the ecosystem approach. Therefore, it's a place for collaboration among stakeholders. Therefore, it facilitates the development of pilot tests, new projects with mobility innovation. The second aspect, the second approach, or let's say tool, which is provided, is so-called digital twin. The digital twin is basically a platform where simulations about the impact of new services and in general of innovations can be tested by groups of stakeholders. And last but not least, we have the third approach, the third, let's say, pillar of the Mobility Lab Helsinki, which is represented by the testbed. Basically, the environment created by the Living Lab is supposed to enable real-life testing of innovative solutions, not only in protected environment, but also in real urban environment, of course, using all the possible tools, regulatory and technological, that can enable these testing and experimental practices. A second example of Living Lab strategy or approach, we wanted to, let's say, combine with a more technological one with the Helsinki Mobility Lab, is the framework provided by the Sunrise project. in which it has been developed a concept for the so-called neighborhood mobility labs. Neighborhood mobility labs are, let's say, typically bottom-up developed living labs where stakeholders are engaged from the, let's say, analysis of needs and opportunities up towards the co-design and the development, the experimentation of new concepts and new services. Therefore, it's not necessarily a context which is framed into a, let's say, a technological system, but it's rather focused on social aspects, on bringing together different stakeholders and creating innovative communities around mobility options and mobility opportunities. So as you see, in literature, there are several definitions, several classifications of what a living lab is. In the guideline, you will find some useful examples in the good practices part, but also you will find an original interpretation or original combination, let's say, of different interpretations that can be applied to the SAMP cycle in order to give let's say, an overall experience on the topic of local engagement, which is considering the different aspects, both the social and the more technological ones. As I said, the second pillar for our guideline is represented by the regulatory sandboxes. Regulatory sandboxes are policy instruments, which are made in order to overcome those challenges or those barriers which are generated by technological transformation, where a regulatory framework is not existing and has to be adapted, but this cannot happen in a short time, and therefore the risk is to jeopardize the potential of testing and, of course, further improving technological innovations. Usually it's composed by a set of special rules or a temporary loosening of some of the rules which let's say, regulate the mobility sector. So from the road regulation to the digitalization limitations, etc., or passenger rights, etc., etc. Therefore, regulatory sandboxes are those virtual places where different sets of rules temporarily apply in order to enable the testing of the mobility innovation, and which is very, very relevant for the testing of innovations in the field of MaaS, in the field of CCAM, in the field of VPAR. Here we have, in some cases, which we highlighted, a national approach to regulatory sandboxes. And this makes sense, of course, because in general, the level which is mostly engaged is the national level of regulation, which has to take into account different possible loosening and temporary modifications in order to enable tests and pilots at local level. We have two main experiences that we have analyzed among other tools in our guideline. The first one is the example of the mobility lab set up in Austria, where, as you can see, in different areas of the country, different labs have been implemented, and providing in some cases research infrastructure in order to develop mobility solutions. In other cases, develop testing environments, and in other cases, again, let's say creating a sort of ecosystem. So it's a concept quite in between living lab approach and the regulatory sandboxes. The element we wanted to highlight is that the national coordination enables to define new approaches and new common rules for the definition of the concept of regulatory sandbox at national level. And this is absolutely an added value for the development of different tests and different pilots on different elements of innovation for mobility, but on the national level. The other example, very, very focused as well on the concept of regulatory sandboxes, is the so-called Riallabore initiative in Germany. In this case, the focus is on creating those regulatory instruments that can, let's say, generate temporary regulatory sandboxes for the development of innovations. And therefore, the Riallabore project, the Riallabore initiative, focuses on the development of new experimental clauses connected to the national law, to let's say the possibility of integrating these clauses in the legislative processes in order to, let's say, modify the regulatory process, not only the regulatory framework, and provides as well a guideline to public stakeholders on how to formulate those experimentation clauses, which are at the basis of the regulatory regulatory sandbox, which has to be established before testing certain kinds of innovations. The third tool, or well, the third pillar on which we are building our guidance, is represented by the citizen science approach, which is a public engagement process which has been promoted at European level, which consists basically in fostering the active participation of citizens to the scientific development in various ways. So, putting together, contributing with their participation and intellectual effort and sharing of knowledge and capabilities, and also by being active in the phase of collecting and analyzing data and information, which is very crucial in order to deliver innovation in the mobility field. So activities under this pillar are very, very various, and this is really, let's say, an open chapter where we can, of course, decide what is the define what is the potential of this tool, and of course be aware of the possible trade-off between say a more participative scientific analysis process and possible, of course, let's say non first best analytical results. Therefore, the application of this kind of tools have to be very, very focused on the specific objectives you want to reach, and on, of course, the need for a broad participation and qualified participation in order to let's say built on effective and consistent resources, but it has a very high potential in terms of dynamics of continuous engagement and continuous gathering and analysis of knowledge and knowledge bases. Two examples here as well. The example of the Herrenberg city, where a digital twin has been developed in order to interpret and to analyze the main phenomena related to the development of the mobility systems. And this is based on, let's say, four main aspects. The first one is the development of a low-cost pre-built sensor in order to collect a range of data on air quality, traffic, etc. The second and landscape. The second one is the application of a volunteer geographic information, the development of this of a information system called the Realabor Tracker, which is basically an app which collects information, visual information on mobility infrastructure, etc. The third one is the development of a visualization and simulation environment, basically the interface, of course, is the development of participative and collaborative planning practices based on these data which have been collected and the visualization which can be provided. Therefore, it's very important, it's very interesting and very composite project, but that has, in my opinion, the great advantage of engaging citizens not only at the level of their wishes or their expectations, but really on the level of better knowing the phenomena and planning on the basis of an enhanced knowledge in a say participated way. The second example is the example of the project We Count, a project coordinated by police. And in this case, the objective of the project is to identify a smart way to combine traffic data and air pollution data, and therefore a specific technological kit has been distributed by citizens who are directly in charge to detect, to collect the data for the interpretation of this phenomenon. So, as I said, we have three pillars on which, for each of them, we have collected experiences, information, let's say also specific guidance on how to implement stakeholder engagement into innovation processes. And what have we done? We have created a step-by-step guidance, which is using a mix of these three main elements, providing opportunities for the application of participatory principles across the main phases of the SAMP cycle. So what you will find in our guideline, basically, it's a specific step-by-step guidance which follows the more or less the main aspect, the main steps of the SAMP cycle, and provides you with suggestions on how to use, how to implement living labs, how to use regulatory sandboxes, how to rely on citizen science initiatives to plan, of course, innovations in the field of MaaS, in the field of CCAM, and in the field of UBA, as stated by our project. I don't know if you have questions on this document, which will be available, of course, on the project website. If not, in the meanwhile, I get ready with the other presentation I'm in charge, which is related to the living labs for mobility innovations.
Thank you, Gabriele. Yes, I think you can continue with the next presentation. It's okay.
Okay, excellent. Okay, so coming back from to the beginning of our presentation, we decided to combine this presentation on stakeholder engagement with the specific experience in building and animating a living lab, which two partners of the SharePlace project, the Mobilissimus and the city of Zalaegerszeg experienced during the project on a specific topic, which is the topic of developing a demand responsive transport service, basically from scratch in an area where no public transport was available before. Therefore, facing engagement, but also practical, operational, and technological challenges at one time, and engaging, of course, a broad range of stakeholders, starting really from the users. Here's just a very short introduction on SharePlace, which had 6 pilots, just to tell you what were the topics. Basically, we have 3 ranges of topics. The first one was the digitalization in Ulm and in the city of Osijek, a multimodal platform, a multimodal transport data platform has been developed within the project, and applying the living lab principles, so engaging stakeholders in the construction of these kind of tools, which are basically the basis on which mobility as a service services can grow and can be implemented. The second range of living labs focused, again, one in Osijek and one in Bergamo, on the development of carpooling initiatives, and a third one focused on the implementation or enhancement of demand responsive transport services. So in that case, these 3 kind of mobility innovations were implemented starting from the establishing of a living lab, which was able to engage the main stakeholders on it. In Zalaegerszeg, the living lab generated the idea of Zerg. Zerg is the mountain goat in Hungarian. And this idea, of course, this name comes from the fact that this demand responsive transport system has been applied, has been implemented in a rather hilly and rural areas. So this is the framework condition. So hilly areas, narrow roads, lack of public transport, long walking distance, high motorization, and of course, let's say a quite relevant urban sprawl. This is the way the stakeholders have been classified and then engaged according to methodologies which in the project have been elaborated by the University of Ulm. Therefore, there is also a common methodology for the stakeholder engagement, which has been developed, let's say, ex ante and then applied to the different pilot sites. As you can see, the target group is indeed represented by the users. Stakeholders which were identified include, of course, the transport providers and the municipality, but also and especially the local local policymakers in order also to test the scalability and replicability of this concept. Here you can see all the steps which followed the development of the project. We can go quickly through them. So we started with the co-design workshops, engaging policymakers and technical participants. A survey has been developed in order to make a first contact and know better the situation of the target group. Some field trips have been organized also to, let's say, test the potential of the service and the potential acceptance of the service by the target group. Living lab activities and workshops have been then reproposed before the pilot launch in order to fine-tune and to define the operational aspects which had to be then implemented for the test. And the service was launched. A first test period was actually very successful because it gathered the interest of several communities, not only the one where it was tested, but also other test areas. This was the level of usage, customer satisfaction, and coverage of the territory. Another aspect which was important in the economy of the project was the idea of integrating the DRT within the existing network. A passenger survey has been developed for the users in order to fine-tune the main aspects of the service before the second testing period. Second testing period, again, based on let's say no charge, but could let's say identify what were the specific characteristics of the service in order to make it more sustainable. Of course, the service was sustainable in the first phases and in the testing phases, also because it was free of charge, but the optimization of the solution was also based on the possibility of, let's say, making some elements of the service a bit more steady and fostering the integration with public. So a second passenger survey was implemented, specific visual information in order to ease the participation and the knowledge about the new service. This is another element. So new schedules, new timetables, etc. And at a certain time, a specific booking system has been implemented. Booking system was for sure very useful in order to know better the characteristics of demand and to fine-tune the characteristics of the supply. What was probably, let's say, still remained as a challenge for the project at the end, and is expected to be, let's say, taken over within the living lab approach, is to elevate the level of integration, engaging new stakeholders and engaging actively stakeholders at a higher range. Therefore, the regional bus provider, the national railway, and so on, in order to enable a higher scalability of the concept. So the concept has proven to be very successful, to have potential also for further investments. But therefore, in this phase, the living lab experience needs to be scaled up and needs to engage new stakeholders at a different and more strategic level. So I hope I was, let's say, comprehensive enough on this specific case. I thank our colleagues from Mobilissimos, which provided us with all the information, and unfortunately could not be here for sharing and commenting the presentation. Any question?
Thank you, Gabriele, for your presentation. Your presentations actually really great to see, to hear. I don't think we have any questions, so I think we can continue and close the session. Of course, this training, this guidance on our tools will be available together with tools in our website and channels, and hopefully we can gather some questions from the people who we are addressing with our tools there. Thank you so much.
Thank you.
Let me share my screen again. To close our webinar today, we just would like to make you aware of our SMP Competence Center for Central Europe as well. Okay. And so our audience can know where to find the tools that have been presented today, as well as of course this training and more material from the Dynaxibility and of the projects that we've mentioned. So this is a platform which we would like to highlight to all of you and invite you to join, to access. It provides knowledge, resources, and support for SMP development and innovative mobility in Central European countries, which is the program area of our project. So you can find the site at smp-central.eu. And we would invite you to browse through it. We're adding more and more content every day. You can find specific information on the different countries in the program area with the national policies, links to the national CiviNet and expertise catalog for each of the countries. As well, there's news from the project Dynaxibility4CE, but also from other projects and other websites. So we have developed a crawling functionality so that our audience in Central Europe can see also interesting news on SMP and mobility from sites like LTs and projects like Reveal or the connected automated driving.eu site, for example. And these are automatically translated to all of the program languages. You can also find good practices which refer to all of these relevant topics for SMP development, such as clean fuels and vehicles, integrated planning, mobility management, etc. But also now through the Dynaxibility4CE, these 3 topics that we have addressed, CCAM, MaaS, and UVAR. So you can find information of each of those, and there's a really big good practice collection which can be useful to watch, over 40 good practices. And each of them has its own site with description and links to interesting information, as well as some tools and resources from guidance on how to get funding, SMP guidance, teaching material. For example, this training will be uploaded also there. So we'd invite you to have a look at it. All of our deliverables and tools will be available in the site as well. And I think with this, we can thank everyone for being here, for viewing also the recording afterwards, and all of our speakers. Very much thank you for joining us. It was great to hear from all of the work that was done in Dynaxibility and in the partner projects. some information on our social media, which we encourage you to follow. Thank you very much, and we can close the event here then. Thank you, everyone. Bye-bye.